Right. Good afternoon, everyone. So I'll be talking about the problem of revenue maximization in combinatorial auctions, and specifically on a class of combinatorial auction problems where buyers are single-minded. So this is a joint work with my advisor, Professor Bruce Hayek. And the focus of the talk will be more on giving a high-level idea of the work we did at the cost of being less precise mathematically. So consider the following example problem. Suppose FCC is trying to sell multiple licenses for using spectrums, and there are players like AT&T or Verizon who are interested in buying those licenses. So each of them will have a very good idea about the market, and they can estimate how valuable a particular bundle of licenses are for them. So this value is the maximum price that they will be willing to pay for one particular bundle of licenses. So key thing here is that this value is a private information, so it's known only to that particular buyer, and they can use this information towards their advantage. So they can misreport this value if it's beneficial for them to do so. So the problem here is to maximize the revenue under this strategic behavior. So we study problems like this under an abstract mathematical framework. So a possible approach here is to use combinatorial auctions, where in a combinatorial auction, it allows buyers to bid for different subsets of items or different bundles simultaneously. And it provides an incentive to buyers to reveal their true information. And at the end, the allocations and the prices of the auction are based on the competition among different buyers. However, this particular approach has few limitations. So one is the implementation issue. So for a general combinatorial auction problem, finding an allocation requires solving a very hard optimization problem, and it's not feasible to solve that problem for large number of buyers or large number of items. Second issue is a communication overhead. So each buyer will have to report the value for different bundles that they are interested in, and this grows up exponentially with number of items. In addition, the revenue optimal combinatorial auction is not well characterized, and the most general result known in this area is for one-dimensional problems, by which I mean that buyers have one real number that they can misreport. So example being single item auction, where each buyer has a value for that particular item, and he can misreport the value for that item. But a general combinatorial auction problem is multidimensional. So a buyer will have different values for different bundles of items that he is interested in, and that makes this problem like hard to characterize. So single-minded buyers are a special class of combinatorial auction problems which are more tractable. So here, each buyer is interested only in a specific bundle of items and has a value for it. So any allocation of items to him that contains his specific bundle, that does not contain his specific bundle, will have a zero value for him. So an example being, let's say suppose someone is interested in a pair of shoes. So if you give him just left shoe or a right shoe, it's worthless for him. But if you give him both pair of shoes as well as something extra with it, he'll be happy with it. So that's what I mean by single-minded buyers. So clearly this has a low communication overhead. That's because now each buyer will be reporting only the bundle that he is interested in and the value corresponding to the bundle. And our focus will be on single-minded buyers for the rest of the talk. So now natural question is, why study single-minded buyer model? So a key issue is complementarity. So combinatorial auction problems are hard to solve because of complementarity among the items, by which I mean that a buyer might prefer a bundle as a whole rather than the parts of the bundle. And single-minded buyers are an extreme case of complementarity, where they are either interested in the entire bundle or nothing. This may seem as a simplifying assumption, but the problem is still non-trivial, and that's because it's a two-dimensional problem. So a buyer can misreport his bundle as well as the value for it. So there's no general known result even for two-dimensional problems. And there are some real examples where buyers' behavior are single-minded. So one of them will be auction of communication links in a tree. So we made the following contribution here. So we study a discrete revenue maximization problem for combinatorial auctions. And this is a departure from traditional models of economics, which is primarily continuous time. continuous values. And some of the results from continuous value model do not carry straightforward to discrete values. As I mentioned earlier, even the problem of single-minded bar is two-dimensional, and there's no general result known for it. So what we do is find a sufficient condition under which we characterize a revenue optimal auction. And this sufficient condition is fairly intuitive. So roughly, it says that a larger bundle should have a higher value. We finally reduce this entire problem into a maximum weight independent set problem, and we provide a simple graphical construction for computing these weights. So we work with the following model. There are n single-minded bars competing for S items. The private information of each bar consists of the bundle that he's interested in and the value that he has for that bundle. We work with the Bayesian model, where we assume that a bundle for buyer n is a realization of a random set Bn, and the value that he has for that bundle is a realization of a discrete random variable xn. It is assumed that this joint distribution of Bn and xn is a common knowledge, but not the specific realization. So specific realizations are known only to that particular buyer. And this joint distribution is independent across the buyers. For rest of the talk, I'll be using this notation of bool b and x to denote the reported vector of bundles and values, also called the bit vector. And this is not the true values for each of the buyer, but this is what they report. So this is the reported bundle and the reported values by all the buyers. So an auction mechanism is specified by two components. One is the allocation rule, which in our context is the probability distribution over the subset of buyers. So what it says that given a bit vector, what is the probability that a set of buyers will get their bundle simultaneously? And the second component is the payment rule, which specifies the payment that needs to be made to the seller by each of the buyers. And both this allocation rule and the payment rule is a function of entire bit vector. So, and finally, the payoff of buyer n is simply the value of the allocation for him minus what he pays to the seller. So at a very high level, we first model this entire problem of revenue maximization in a combinatorial auction as a optimization problem under constraints, where constraints are following. So the very first thing is that allocation of items should be feasible, by which I mean that if the set of buyers should have a disjoint bundle, otherwise you cannot award them their bundle simultaneously. Second is that the pricing mechanism of the auction should be such that buyers should be truthful. So they have an incentive to reveal their private information truthfully. And there is a known result in economics called revelation principle, which says that this can be done without loss of generality. The third constraint is voluntary participation. So you cannot really force a buyer to participate in an auction and charge him any arbitrary high amount of money. And what it says that a buyer will participate in an auction only if his payoff from participation is at least not negative.
So under the voluntary participation constraint, why would a buyer report a wrong bundle that he's not interested in? Because if he participates, then he's forced to. So he just lies, and then if he has to pay some amount, then he won't pay at that time.
No. So is your question that why he would lie under voluntary participation, or?
Why would he lie about the bundle? I mean, you said that he's allowed to
So.
About the bundle as well as the valuation.
Right. So there is a joint distribution on both bundle and the values for the bundle. So what a buyer might do is that he might misreport a different bundle depending on the structure of the auction mechanism. That may increase his chances of either getting the item or paying a less price for the items he's interested in.
Probably a larger bundle, right?
It will always be a larger bundle for single-minded bar context. Yes.
Is there a charge for participating in the auction?
No, there's not.
So by participation, you need credit.
Sorry?
A buyer participates in the auction when he bids on an item.
Right.
But not zero. If you get
I mean, if you don't get your item, then you don't pay anything. So.
Well, once you get an allocation
No. So this is one-step auction.
For this price.
Yeah. So you can do like multiple step auctions and things like that, but the problem that we are considering is one step. So it's like everyone submits their bid, and the allocation and prices are decided. So that's the final at that point. So and finally, we obtain a sufficient condition under which this problem can be solved. And so the sufficient condition requires a definition which is hazard rate ordered. So what it says that if there are two random variables, Z1 and Z2, then Z1 is less than Z2 under hazard rate ordering. If you condition them on some Z hat, then the tail probability of Z1 should be less than tail probability of Z2. So what it says that higher mass is assigned towards a higher value for Z2 as compared to Z1. And this should be true for all Z and Z hat. Now consider two bundles where one is contained in another. So here this bundle S is smaller than bundle T. Then Xn condition on the smaller bundle. So Xn here is the value of buyer N for his bundle should be less than Xn condition on a larger bundle. So this is under hazard order sense. So what it means is a larger bundle should have a stochastically higher value. And this condition seems intuitive for single-minded buyers. So under these, the final structure, sorry, yeah.
Is that stronger than stochastic order?
This is stronger than first-order stochastic dominance. So hazarded order in turn implies first-order stochastic dominance. So finally, under these assumptions, the final structure of the optimal auction is following. So we first construct a conflict graph where there's a node corresponding to each of the buyers, and there is an edge between two nodes if the reported bundle of those two buyers are in conflict. So if they're not disjoint, then you draw an edge between those two buyers. Then you assign a weight, which I call as virtual valuation, to each of those nodes. And key thing to note here is that this weight is a function of the reported bid of only that particular buyer. So it does not depend on the bids of everyone else. And finally, the set of winners are a maximum weight independent set of this graph. And the payment that a winner makes is a minimum value that he needs to report to still win. So it's actually less than what you report. And this ensures truthfulness. So the virtual valuation that is used as a weight for the graph that I talked about can be constructed graphically as follows. So,
Can you go back to the previous page?
sure.
So you fix everybody else's bid and then reduce yours.
Right.
Such that you're still part of the max weight independence set.
Right. So it will be your minimum value at which the maximum weighted independent set containing you will be higher than the next best maximum weight independent set. So now the virtual valuation can be constructed graphically as follows. So I'm just talking about one particular example here. So suppose condition on this bundle Vn, the value that a buyer N has can take 4 different values, x1 to x4, with probabilities p1 to p4. Then what you do is draw vertical lines like these, separated from each other by p1, p2, p3, and p4. And then you draw negative x values. So this is minus x1, minus x2, minus x3, x4, and connect them to the end point. So you draw these lines. And finally, these slopes that are the intersection points are the virtual valuations. Small issue here is that if these slopes are non-increasing, are not increasing, then this resulting graph is not convex. In that case, we take a convex hull of this and use these slopes as the virtual valuation. So this is how you compute the virtual valuations and use it as a weight for maximum weight independent set problem. So this completes the description of the resulting auction mechanism. So any questions up to this point? So just concluding, so we characterize a revenue optimal auction for single-minded buyers, and the resulting auction has a very simple structure. And one issue here is that finding maximum weight independent set problem is still NP hard, but at least for single-minded buyers, it's easier than a general combinatorial auction problem. And Also, there is a square root s polynomial time approximation for finding out the allocation. And anything better than square root s is, again, NP hard. And we work with discrete model here, but all the results here can easily be extended to continuous models. So, yeah. Any questions? Yeah. It's a good question. So we have been trying to figure out a way to come up with virtual valuations without going into mathematics, but I don't think we really have a very good answer to this, except for the case of maybe, let's say, there's only one buyer, then it actually can be thought of as a marginal contribution to the revenue corresponding to each of the different values that they can take. But I don't think that there is a very good answer to this question, except for going into the entire math and getting the final expression. So
that's kind of been an open question for about 28 years, actually, since Meyerson's paper in 1982.
Right.
But for simple examples in Meyerson's paper, at least for Meyerson's result, you have some intuition as to sort of if a person on average values an object highly and then a bit too low, you're sort of adjusting for that. Similar interpretation holds here too, probably, right?
So the only thing I have seen people talking about is essentially talking about the total revenue that a seller extracts from a buyer, and then assigning them as a marginal revenue corresponding to different values that you can take. And that marginal revenue is actually virtual valuation. So in a sense that you are partitioning the entire revenue that you can extract from a buyer and assigning that what fraction comes from what values. But this did not really answer the question that why this particular approach is optimal. Anything else?
So the polynomial time approximation that you mentioned, so if you do that, it still satisfies all the constraints.
Yeah, it still satisfies all the constraints, which is very different from other results in auction theory, because most of the time whenever you try to approximate any allocation rule, then you will break constraints like truthfulness or voluntary participation. But in this particular context, there is a polynomial time approximation which still satisfies all the constraints.